Good morning, good afternoon, good evening, wherever you may be. We are welcoming you coming into today's session for our Chief Scientist Distinguished Lecture Series. We have a couple minutes before we get started, so just again, get on in and get cozy. Thank you so much. We'll be beginning in about 2 minutes or so. As we are getting started, if there's any questions that you may have for our speaker, please put that into the Q&A feature located at the bottom of your screen. And at the end of the session, if time permits, we will go ahead and open it up for Q&A. So again, thank you so much for being here. We'll just getting everybody into the virtual room here. It's a great day, sunny weather and nice on the East Coast here. Again, we're allowing folks to come in. So good morning, good evening, good afternoon, good day, wherever you may be, because we are a global organization. We like to recognize that there may be many people joining from different areas of the world. So thank you for joining us. As a quick housekeeping note, again, this session is recorded. It will be available on YouTube after it goes through our public release. Also, the presentation itself can be available. Please email me. I will put that into the chat and I'll get that over to you as quickly as possible. So with that being said, I would like to turn it over to Dr. Kanamara Doran, representing our Chief Scientist Office. Over to you, ma'am.
Thank you so much, Cindy. Welcome to the Chief Scientist Distinguished Lecture Series. This is the premier lecture series for the Air Force Office of Scientific Research. The series is put together with the help of the Chief Scientist Office, but primarily through the work of the program officers and international program officers at AFOSR. They invite distinguished senior academic scientists from across the universities and industry landscape who are doing breakthrough scientific research and work in engineering and mathematics. So today, Eric, our program officer, is going to introduce the speaker, and I hope you enjoy the discussion. Thank you. Over to you, Eric.
Okay, thank you. It's my honor to welcome the audience to Dr. Vahid Tarokh. He has an amazing background. He started with Bell Labs, and in 2000, he left Bell Labs to become a professor at MIT. From there, he quickly joined Harvard University and was named the Gordon McKay Professor in EE, also a joint position with the mathematics department. In 2018, he left to join Duke University as the Rhodes Family Professor. And then he has assignments where in 2018, he was a Gordon Moore Distinguished Scholar at Caltech, and he served as the Microsoft Data Science Investigator at Duke University. That's what he put in his bio. However, he has a fascinating impact on the community to get to these distinguished positions. He's a fellow of many societies, and he's a member of the National Academy of Engineering, which was not listed. And he is well known in the community for space-time codes for high data rates and wireless communication, which from his originating work in Bell Labs has now forged the directions in, say, 5G and 6G communications. And with that, he has been working on recent tasks for AFOSR on insect analysis, deep learning, and cognitive radar. So hopefully this should be exciting and entertaining. And please put your questions in the Q&A because we'd like to have him respond to your specific interest in the topic. Over to you, Dr. Tarokh.
Thank you very much for your kind introduction. Let me see if I can make this full screen. First of all, I want to thank Dr. Blush for arranging this. Dr. Doran, really appreciate you, and Dr. Roach also, that is not here. I know he's very busy. And Ms. Barner really put a lot of effort. I want to thank everybody in U.S. Air Force, AFOSR, U.S. Space Force, AFRL for financial support and also mentorship. I mean, Many of you guys actually gave me ideas, and not only Air Force, I'm also indebted to ONR, ARO, DARPA, DHS, NSF, and NIH. And all of the program managers there, wonderful people, US taxpayers, all of them that supported me, giving me the opportunity. I mean, I realize you have choices, and I really appreciate that you gave me the chance. And really thank you for your mentorship, especially Eric. Eric really sometimes give me ideas that are really profound, and I want to thank him for educating me. Thank you all for educating me. I'm also fortunate to have multiple members of the active members of the US military working with me. One of them was introduced to me by Eric, Lieutenant Matthew LaRosa. He's a US Air Force pilot. And of course, Major Kuiper that you see at the top, he's actually right there in Baghdad in the background. And both of them work with me. And I am very fortunate to have them as my PhD student. So I want to thank you for enabling it. Thank you for supporting Lieutenant LaRosa and Major Kuiper. And I'll talk about a little bit about what we are doing. It won't take more than a minute. Multiple activities that are supported by Air Force. I only mentioned those because this is an Air Force and a Space Force talk. One of them, of course, I owe a lot to Patrick Bradshaw. Dr. Bradshaw have been educating me about insects. And what he's interested in is not just the insects. It's like fascinating how a moth with such a small brain can encode the environment, everything that it sees, make such quick decisions, run away from predators. And we are trying to understand how the brain of moth represents the environment. And that's what Patrick's interest is. I have been fortunate to be educated by all of these distinguished insect scientists that I work with, neuroscientists. And for instance, Jeff is teaching me about how these insects smell the environment. And that's like really fascinating. So again, whatever I talk about and whatever I have done is because of my colleagues and my students. So, and this is one of the opportunities that are given to me. I really thank you, Patrick. Also, I am working with Dr. Frederick Leave, Dr. Fariba Fahru, and Ali Sayer on more or less understanding extreme events. I'll talk about this later in this talk. I intentionally chose that because I know Eric likes math. I'm going to show the math without going into math. And again, multiple people here have been educating me, and the students have been educating me. I've been very fortunate. Another thing is that the COE at AFRL and AFOSR, Dr. Don Wagner, actually Wagner has supported us. It's going through Rob Calderbank, my colleague. But there I try to understand how you could encode the environment to figure out if there's an adversary there or adversarial activities are changing in nature. And we'll talk a little bit about that. And of course, Dr. Eric Balash has been supporting me on, as he said, cognitive and what I would call data-driven STAP radar. And I have been very fortunate to work with Dr. Rangaswamy and Dr. Sandeep Kuginini. All of those are, and this wouldn't have been possible without Eric putting me in touch with them. And Eric himself gives us very good ideas. And actually, I'm very impressed. He reads the papers and gives us comments. Usually, he puts a lot of effort into this, and I really appreciate him. Finally, the last effort that we are doing, this one is not directly going through AFOSR and AFRL, but it is going through Raytheon and Pratt & Whitney. And what we are trying to do is look at titanium alloys. And if we can get these EBSD images, then we want to look at the fabric of these EBSD images and say, if you load it in some way, how long is it going to last? And this is what we are working with Pratt & Whitney and Raytheon on through a contract that is given to them by AFRL. Of course, I'm 2 levels down. Raytheon is a subcontractor of Pratt & Whitney. I'm a sub to the sub. So just a disclaimer that what I am going to talk about today is just my own opinion. It does not reflect the views of the US Department of Defense, obviously. So what I am interested in is representation. And I want to motivate that without going through math why we are doing this. If somebody tells you to calculate this multiplication of Roman numbers, and Romans had an advanced civilization. They had a Roman numeral system. But if I tell you to multiply these two numbers, I would say, everybody would say it is not as easy. So why is that? Because the way that the numbers were represented using Roman numeral perhaps made it difficult, right? The representation was not very efficient. Now, Greeks come before Romans, so I would say that these three guys, Archimedes, Pythagoras, and Thales of Miletus, were probably some of the first military researchers that use math and physics to kind of build military equipment. In the siege of Syracuse, for instance, they used their equipments against attacks. How did they multiply? Obviously, this representation wouldn't work. So the way that they multiplied, I am told, is by geometric representation. You use the Thales theorem. You have two lines that are in parallel. So if I put 1 here, and A here, and B here, now Thales theorem would say 1 to A is B to AB. So this line length would be A times B. That is how these people even integrated. They did it geometrically. I mean, Riemann sum was used by ancient Greeks, but not, of course, in the same notation. But this is another representation of the same thing. So is it more efficient? It's for you to judge. Then there comes the decimal system. Now, one can argue that the decimal system has been a huge advancement in human history. I mean, you go to the primary school and you'll have to deal with multiplication and addition tables using decimals, maybe a few years of your life. A lot of human lives, if you think about 7 billion people in the world, each one of them possibly putting 2-3 years into learning, doing arithmetic with this, that is 21 billion years, roughly, is put into working with decimals. Obviously, a lot more efficient than this and this, the Roman way and the Greek way. But is this the most efficient? Well, decimals are there because humans use their 10 fingers. But if you look at computers, computers use binary representation. So it's only 0 and 1. So if you think about that, if you use our 2 hands, the multiplication table would be very easy. Just 1 times 1 would be 1, and everything else will be 0. So imagine how many billions of years human beings would have saved if they would have trained with binary numbers. Computers use that. Is the binary numbers the best way of doing it? That remains to be debated too. But what we learn from here is that what makes a representation desirable is it's the ease to work with it. So you want it to be not too complex to work with. No, I could make the problem more complicated. I have data I want to represent. I want to capture the essence of phenomena, signals at hand. I want to describe a complex phenomena as compactly as possible. That's what an information theorist wants to do. And we want to be able to generalize that we want the science to build on the top of each other. That's why we have all of this archival work. We cite each other. Representation of knowledge should be such that you build on the top of each other. And finally, we like it to be interpretable to some extent. Now, Dr. Bradshaw always looks for interpretable representation. If I could figure out how to process the data that the moth sees, but is it going to be interpretable? That is a question that also is very legitimate and we need to answer. Now, talking about what I do, I want to motivate it first by linear representation. Now, in statistics, you have regression, autoregression. These are linear methods, very popular because they're simple, easy to analyze. And in signal processing, you have Fourier representation. Fourier representation, the Fourier representation is a linear representation, and it is interpretable. You get the signal, you get the pulses in frequency domain, right? If you look at Parseval theorem and Poincare theory and all of those things, and you do them, you'll see that really the time domain representation and frequency domain representation are equivalent, because you go to time to frequency with Fourier, you come back from frequency to time with inverse Fourier. So it seems that Fourier representation shouldn't be able to do anything because they're equivalent to time representation. The temporal representation and frequency representation are equivalent mathematically. But then you go to video coding, image coding, you see that it works. It does a lot better. So the key that makes this Fourier representation work is the fact that the underlying signals, like if you think about my image, or like you think about my shirt, this is a very boring shirt. It's all of it the same color, except a few buttons. Therefore, the number of frequencies that exist there are not that high. Very high frequencies have very little power. So you could use that to represent in a more compact way. So what we learn from here is that the representation should also match the data. Natural images, natural speech are good for Fourier representation, although mathematically, Fourier and not Fourier should be the same. Temporal and frequency should be the same. Now, key advancement comes by Andrei Kolmogorov and Arnold, his students, that they showed that a lot of transformations can be written by composition of simpler transformations and they come up with so-called universal coding term. So fundamentally, what they showed is a single layer neural network approximates any continuous function, multivariable continuous function on a compact set. So, and actually, if you put some conditions on the function, this approximation is exact. I mean, obviously, the neurons that they choose are not what we use in today's deep learners, but more or less, it gives the essence of deep learning, more or less give it to you, right? I mean, so what happens is that they showed that these nonlinear representations also have potentials. Of course, before that, McCulloch and von Neumann and everybody tried, and they did some advancements on neural network. We cannot say that Kolmogorov invented it, but Kolmogorov-Arnold shows that more or less it should do the work. Now, recently, this nonlinear representation learning has been a very popular topic. It's not as interpretable in many cases as Fourier, but it does work on natural images, natural speech, language modeling, all of these things. So here is an example. Here is the advancement of deep learning on ImageNet. What you're saying is the top 5% error in 2010 was above 25%, like 28. And in 2017, now it is about 2%, less than 2% actually now. And it beats the human performance for classification. So what we see is that these nonlinear methods are coming and replacing the linear methods in many, many cases. Of course, Fourier transform and Fourier series still are very valuable, but they are being replaced due to this advancement in computational methods that we have. We couldn't implement Kolmogorov's universal theorem, universal approximation theorem 50 years ago because there was no computation power for it. But now the computation power processors are there. And even in generation of images, sampling, you will see huge advancement. In 2018, this is a paper by Karas et al. I took the images. You see how realistic the images are. And with the advancement of diffusion models, now it's even more realistic. And big gun of Google generates human images that are almost perfect. I mean, you could not say if it is fake easily with your eyes. So therefore, we see that representation learning is going through a revolution by becoming nonlinear. And that is the interest of my group. So although the projects that I mentioned are very different, brains of insects and data-driven radar don't seem very similar, but I argue that they're all about learning representations. How the brain of insects represent the environment. How can you represent the clutter in radar using topographic data? That's what Eric supported and we're doing. And using that, improve the radar performance. How to learn the representation of a communications environment so that if something changes, you could say this is out of distribution. So some adversary are here. And how to try to figure out if an extreme event is going to happen in a time window. So we have to look at the phenomena. We have to look at that EBSD image and see what is there, how to represent it to make a definitive conclusion. So today I'm just going, because of time limit, I'm going to talk about only of my team's work, about my team's work on the last topic. The reason that I chose this topic, because the mathematics of these things, frankly, are brand new. That means that if you really think about the last term that I'm going to show you that I'm going to use to build neural network from it, the guy that came up with the term is still alive. In mathematics, it means that the field is very new. Hopefully you all will see and agree with me. So why am I interested in extreme events? Extreme events are events that happen with very low frequency, but they have great impact. I mean, think about the Fukushima reactor and the tsunami. Doesn't happen that often to see an 8 Richter earthquake there and a tsunami, but what happened shows the impact of it. So if we can figure out something about it, it could be very useful. Other extreme events, financial crisis, violent conflicts, wars, hurricanes, tsunamis, global warming, epidemics, all of these things are extreme events, could happen spatially, temporally, or both. If you have an idea about the probability of an extreme event, then you could use that to come up with remedies. Maybe you set your insurance rate right, so that if it happens, you don't have to be bailed out by the US government. Or you provision against them. You put a budget and say, okay, we know that the chance there is that a Fukushima reactor type event can happen. Maybe I over-engineer my reactor. I pay a few dollars more or a few $1 billion more, but I make sure that it lasts if something like that happens. One thing that is very interesting is how these extreme events relate to each other. For instance, if there is an earthquake in Nevada, can it affect an earthquake in California? Well, the tectonic plate is connected. So surely there got to be a relationship between these extreme events. Sometimes maybe some non-extreme event in one place affect an extreme event in another place. We want to understand it. Another example in financials, whenever the New York Stock Exchange crashes, you will see that some of the satellite stock market crash, right? So now the question is, can a New York Stock Exchange crash lead to a crash in Hong Kong Stock Exchange? These are the kind of problems that arise when you look at extremes across space or across time, relationship between extremes. Yet another thing that could be useful is that when you're thinking about extremes, you're thinking about tail effects, tail of distributions. Tail of distributions in machine learning could be of huge interest. Like, for instance, much of the generative models of today, because they are trained using non-extreme data, they don't account for or cannot generate that extreme data points of the people that are in the tail. Like, in essence, if you use a GAN and only feed them pictures of regular size human beings, it will have a very hard time to create a person with the height of an NBA player because it hasn't seen it. So the question then is, can we come up with better methods that can generate these tails? So we have to understand the tails. And then if you look at the tails, sometimes it could actually lead you to do better out of distribution detection. If we know that something is natural, there is a tail effect, and something that is not natural, that tail effect is not there because the machine could not generate it, we could figure out fake things from real things. That could be interesting. So therefore, generative models that account for tail of distributions could be of interest too. So in the effort that we are mentored and funded by Fred Leave and Fariba Fahru and Ali Sayer, we have been doing some of this work in the last 3 years, 3.5 years now. And what we are doing is modeling dependence between extreme events. We want to find causal relationship between an extreme event. In essence, you can give me a vaccine and I can get 1 degree fever. And then after a couple of days, I recover. What would be more interesting is not what is the effect of vaccine if the effect is minor on individuals. If the effect is going to kill them, that will be more interesting, right? You want to know if I am given this vaccine, if I am going to die. If you know that there is something that causes that extreme, you want to stop it. You don't give me the vaccine for that. So causality relationship in extremes by itself is super important. Now, another thing is that when I want to, for instance, design against the extreme events, well, if I don't have that much data from extremes, I cannot write a simulator to simulate the performance of my design. Say I made a chopper, I want to make sure that the chopper propeller doesn't get jammed. But I need to simulate, and I need to create extreme-like events. So therefore, you're interested in generation of new extreme events from training data. Now, there could be that the training data could be extreme data. It could be non-extreme data. Like maybe I don't have enough extreme data from Fukushima reactor type earthquakes, but I know 1 notch below. Can I extrapolate? And the other thing is probability of extreme events. Can I say in this time window, the chances of an earthquake of 8 Richter is such and such, approximated? These are the things that we are interested in. Now, I tell you about different kind of extreme things that we do, analyze, and then very briefly, and I just pick up one, which is the simplest one, and then I talk about that. And a little bit technically. I don't want to make this talk all about math. Sometimes the extremes happen, but what I would call a herding effect. For instance, if you look at all of these cattle, they all are doing the same thing. They follow each other. A crash in a stock market can happen that way. Individuals all start selling because they see others selling. But if you talk about seizure, neurons, ordinarily their firing is not synchronized, Suddenly they become synchronized and they create seizure. One way to deal with predicting extremes or modeling extremes is to consider extremes of this type. So we consider all kinds of ways that extremes could be formed. Here, what we are using is so-called Vlasov dynamics. Now, I don't know how many of you are familiar with Anatoly Vlasov. He actually fixed Maxwell equation and Poisson equation and Boltzmann equation, all of them. And unfortunately, he was not given a Nobel Prize, but the guy was great. So the idea was that he observed in plasma physics that the theories that Maxwell and Boltzmann and all of those guys push in statistical physics had a shortcoming. It did not account for long-term interactions between particles. So he tried to fix that by a model that's called a McKean-Vlasov model, because McKean worked on it in the US and popularized it. So this accounts for interaction between particles. So here, the herd are those particles that their interaction leads to an extreme event. And what we have done is that we have come up with representation learning methods, neural network methods that actually model the evolution of data using McKean-Vlasov processes. Actually, if you look at the paper that I have put below, that was just presented actually in AI Stats, you will see that it can beat in terms of prediction of extreme, LSTMs, and many, many other methods that are very popular for temporal series prediction, and almost every other method with limited data. So this is one way that we think about extreme. The second way about extremes that I'll just give a brief discussion about, but I'm not going to get into it, just like the first one, is about excursions. So you could think about extremes that are only of interest if the event that you're looking at goes above a certain threshold. Like if I'm looking for the flooding in dikes in Netherlands, only when the water goes above the dike, I see the effect on the other side. Can we use this to predict the probability of the excursion in a window of time ahead? Like saying, in a year, there is this much chance that the water goes over this dike. Here we actually built on Ito's work. So Ito calculus is famous, but Ito's excursion theory is not as well studied. I mean, or as appreciated, because it is studied by Ito. So what we do is that we build on Ito's work and do a transformation of it, a nonlinear transformation using a neural network, and fit it to a very general model. Ito's work was on the Brownian motion, and they calculated the probability of excursion. That was done by Levy. But here we are using a neural network to do it in a much more general way. And to the best of my knowledge, we are the only one that can actually do this very efficiently in high dimensions. The third thing that I'm not going to get into that much, but these kind of extremes are also important, is that when the extreme is hidden. So an example of that is the Gleason score in prostate cancer biopsy. So when you look at the biopsy for prostate cancer, you don't see anything extreme in the image, because all of the pixels are between 0 and 255 anyways. So nothing is extreme. But what happens is that there is something hidden there that the eyes of a doctor, a pathologist can see, looks at it and says, the Gleason score is 9, which means that the guy is definitely going to die from prostate cancer. But if it's 1 or 2, it's not as bad, right? So what happens is that the brain of the doctor, looking at the image, does some representation learning. It extracts the essence of this image. And that essence is a random variable that is going extreme if there is a cancer in this image. So that is more or less what we are modeling. And here's a paper that we just published, but there is another paper forthcoming that we generalize that to time series. So essentially, we come up with methods that you extract those essence of these images. And now these essence go to extreme when there is serious cancer, or in general, it could be, for instance, you look at the environment for communications and you see something extreme happens in latent domain, in hidden, and you say that is an adversary. And that's kind of like the idea. Now, finally, I'll talk about what is the simplest version in this talk for the next few minutes. I think I have about 17, 18 minutes at least. So this is the most classical version. People look at extreme events at maximum of outcomes of data. So you have IID data, for instance. It doesn't need to be IID. But you look at like the event, and then you say something is very large, therefore an extreme happen. What is the probability that that extreme happens? Now, if you look at the way that people analyze classical data, they built on the work of Gauss. Actually, it is due to Dumoivre, but it's called Gaussian central limit theorem. Of course, Gauss deserves it. But they look at CLT. They say, okay, maybe the data is IID and I don't know the distribution, but if I look at its average or do something to it, it follows a known distribution, Gaussian distribution. That means that I could apply these things in asymptotic if I have big data to do Gaussian analysis. And that's how they analyze this data often. People do that. It's a universal result, and everybody knows about it. Now, when you deal with extreme, the situation, I would argue, is similar, although the results are very new by mathematics standard. Let me talk about how I use these results to make new neural networks to analyze extreme. The first key concept is the limiting distribution. Do we have something like central limit theorem? Okay, let's go to a casino. I try a dice and I throw it 1 time, 2 times, 3 times. I record the outcomes and I look at the maximum of the outcome. I mean, if I throw this die a million times, more or less, I'm guaranteed to hit a 6. So if I look at the maximum of outcomes, and I call it maximum of n outcomes at m sub n, what would happen is that m sub n becomes a delta function at the maximum value of the supports. Now, we know that the maximum, the CDF of the maximum, is the CDF of individual random variable to the power of n. So if f of x is the CDF of x1, and I look at maximum of x1, xn, that's a classical result. CDF is fn of x, f of x to the power of n. So whenever f of x is 1, which is the maximum of the support of the distribution, this thing goes to 1. Whenever f of x is less than 1, it goes to 0. Essentially, it tells you you're guaranteed to achieve the maximum if you repeat the experiment millions of times, a large number of times, as n goes to infinity. Not a very useful result, obviously. If I go to casino and drop this die a million times, eventually I hit a 6. Is it useful? So something that Fréchet came up with, some idea that Fréchet came up with, but of course, the only person that doesn't have his name on the result is Fréchet, is the idea that what if I take this maximum and I scale and shift it? Can I get something meaningful and useful? Let me give you an example. Suppose I take the Gumbel distribution. I know that the CDF of Gumbel distribution is exponential of negative e to the power of minus x for x between negative infinity and plus infinity. That's the CDF of Gumbel. Now, if I take the maximum of n outcomes of Gumbel, I get f to the power of n of x, and fn of x is given by exponential of negative e to the power of minus x to the power of n, which is this. Now, as you can see, it shifts the CDF by log of n. That means that the maximum is just like one of these guys shifted by log of the number of outcomes. So if I take the maximum and take the log of the number of outcomes away, I get a distribution that is not degenerate. It's not a delta function. It is the Gumbel distribution. So this Gumbel distribution is unique in that sense. Now, let's look at another distribution. It's a Frechet distribution. Now, it takes exponential of negative x to the power of negative a. That is the CDF of Frechet. Now, do the same thing. Take the maximum. The CDF of maximum is this CDF to the power of n. And you would see that now, if I scale the maximum by the number of elements to the power of negative 1 over the parameter of the Frechet, I'll get the same distribution. So a scaling of it, essentially I am compensating for the growth, gives me the same distribution as non-degenerate. So Boris Geradenko in 1950s, he was a student of Kolmogorov. He proved a beautiful result. And the idea is this. Suppose I have n outcomes of the same distribution, I take their maximum. Suppose that I can scale and shift them and I get a non-degenerate distribution. Just like the two examples that we have. Then that non-degenerate distribution is either a Weibull distribution, a Gumbel distribution, or a Frechet distribution. There is no other possibility. And he actually calculated what this scaling and shift version could be. So it is not a central limit theorem. What I would call it a non-central limit theorem. But it can be used for doing neural networks, I'll argue. The second key concept is modeling the CDFs. Now, if here I only had one die. Now, suppose I have 2 or 3, and they're dependent. I have earthquakes, they're dependent. I want to see how the CDF of these guys are together. What's the probability that I see an earthquake that is large in Nevada and California in an interval of time together? Here, I need a joint CDF of events. And what you can do is introduce something called a copula. What you do is that I take the CDF of the original F of these vectors, say Nevada and California earthquakes. They have a joint CDF, it is F of x1 and x2. Then I pick up F of x1 and F of x2, the marginal CDFs, and I call them U1 and U2. So F of x1 and x2 would become F of F1 inverse of U1 and F2 inverse of U2. Now, what's the good of it? Well, the CDF is between 0 and 1. U1 and U2 also now are between 0 and 1. So I get a dependency function that operates on the cube, a compact set. So what happens here is that this copula encodes the dependence between this Nevada earthquake and California earthquake. I know that in extreme, these earthquakes are going to be Frechet looking, for instance. Therefore, I know their CDF in extreme. All I need is to calculate their dependence. And this copula does the dependence. So I'm not going to go into the math, but I am going to say that both the asymptotic distribution of individual extreme events and the dependency of them can be modeled using mathematical structures that are relatively new in terms of mathematical life. And here is a beautiful result by James Pickent. He was a professor at UPenn. And UPenn Business School, statistics department, and he generalized the result of Boris Ganondenko to multiple variables. And the key insight is that the copula of extreme events has a very specific format. And the format is given by the formula that he established. Actually, this proof is much easier than the proof of Ganondenko. Proof of Ganondenko was so hard that it took Fisher, which was a great statistician, Tippett, Frechet, Gumbel. They tried. They couldn't prove that result. So Ganondenko used a differential equation approach to prove it. This one is more straightforward. What he shows is that the copula of these extreme events has a specific format. There is a function that is defined on the simplex. So if you have 3 variables, earthquake in Nevada, Arizona, and California, you have the simplex in 3 dimensions, which is a 2-dimensional surface itself. And there's a homogeneous function defined on that simplex that's called the Pickens dependence function, and the copula has a specific format. This is like the central limit theorem, if you think about it, in higher dimension, that you have a covariance matrix and you have a mean, right? It's vector mean and vector covariance. Here, there is more than just Frechet and Gumbel and Weibull. There is a dependency function between them, and that dependency function is so-called Pickens dependence function given on the simplex. So if I want to understand a model dependency between earthquakes, I have to model the Pickens dependence function. Pickens dependence function is therefore going to be approximated by a neural network. That is the vision that we pushed. We want to build a neural network that models Pickens dependence function. Now, so Pickens died maybe 10 years ago in a ballpark, but here is a guy that is alive, DeHaan. DeHaan proved another result in mathematics that has a value in generation of data. So we use that for creating generative models. And the result is that if you think about Pickens dependence function that is defined on a simplex, it has a format. So if it is d-dimensional, if you want to calculate it at a value of simplex that is on d dimension, what you do is that there is a PDF defined on the simplex, which I denoted here by d lambda of s, and the function, Pickens dependence function, is given by a formula depending on that PDF defined on simplex. So in essence, PDF is what a generative model models, either implicitly or explicitly, like a GAN, try to learn the PDF of a human face, for instance. What I want to do now, so these results both have computational value. One, I want to figure out, can I make the Pickens dependence function using neural network? Or can I make the DeHaan's spectral measure, which is the PDF that creates the Pickens dependence function using a generative model? So these are the things that, for instance, some of the things, the simplest thing that we did in the project that Fred Levy and Fariba Fahru and Ali Sayer kindly supported. And I show you the results of this modeling. The modeling is not trivial. As I said, this is a very new result. Lawrence DeHaan still is alive. And he's, I think, still a professor of Catholic University in Belgium. Okay, so now let's see how we do it. Modeling extremes. How much time I got? 13 minutes, okay. So one thing that you learn from the theorem of Pickens is that Pickens dependence function has to have some property. This property is called Dmax decreasingness. And it is a form of very strong convexity. So what we did, we invented neural networks that are Dmax decreasing. Because we know if we want to estimate Pickens function, it has to be Dmax decreasing. So once we use that property, we need a lot less data to train the neural network. That's what we did. The second thing that we did is that there is a method that actually people that try to estimate Pickens dependence function implicitly built in their papers without paying attention that it could be used for training of neural networks because they weren't interested in computational method perhaps. That you could do to create data, bootstrap the data. So you have very limited extreme data. By sampling from the simple X and doing the trick that they did, you could create a lot more training data that could be used to train a neural network. In essence, with very few extreme data, we could train neural networks in very high dimension using this technique. That's a method of data bootstrapping. And if you use our method and compare it with everything else in the literature, it does the best. So it's a state of art. Finally, in this method, we also come up with a method to actually calculate the Dehaene spectral measure using generative models that people use for human face. For instance, a GAN, or for instance, a normalizing flow. And therefore, now we can create extreme-like looking data from limited data that we have. We train the neural network, we come up with Pickens dependence function, then we can estimate Dehaene's spectrum and create new data that is extreme looking, which is very hard to observe in practice. So these are shown to be making an excellent match with reality. I'll show you the results. So the paper is here, and I must definitely mention Jose Blanche. Jose is excellent, and he was a co-author in this. So let me tell you how we define, how we make Pickens dependence function. The key to the Pickens dependence function comes from the Dehaene's theorem that essentially says that if you sample from a spectrum, you could replace this integral. We replace this integral with an empirical version of it, empirical estimate. And then we showed that such empirical estimation provides a universality result, just like what Kolmogorov did for general neural network. What we prove is that our method estimates any Pickens dependence function. And we come up with a construction that so even a single layer is enough, just like what Kolmogorov proved for general neural network, but we also come up with a multi-layer construction. We prove it is universal, and we do this system designed, and now we have to train it. For training, as I told you, we go to the way that people classically estimate the Pickens dependence function. There is a trick of a transform that we use. We use the same transform, but we showed that the same transform version, when you sample from the simple X, can give you an exponential where the exponent is the value of the Pickens dependence function at that point of simple X. And then we use this to train the neural network. So here is some experiment. There are multiple estimators that existed, and they're a state of art in the literature. And one of them is due to Pickens himself. One of them is CFG, and one of them is called BDV estimates. These are, one of them is from 2011, the most recent ones. And what we do is that we pick up a standard version that people make synthetic extreme events, and those are symmetric logistic and asymmetric logistic models. And what we show is that our proposed method significantly beats everything. You can see it here in estimation of Pickens dependence function, some by orders of magnitude. And you will see that that is good. So here is the error for estimation as the dimension goes large. So when the dimension goes large, you will see that still our method actually works quite fast. In fact, beyond a certain dimension, none of these guys are able to generate new extreme data because it's computationally very complex. But once we use these neural network methods, you will see that I can generate extreme data in any dimension. Here are the data that is realistic. Wind speed in California. We train on summer monthly daily max. We test on weekly maxima. Ozone levels, again, dimension is 4. We train on summer daily max, test on weekly maxima. Commodities, now we looked at max drawdown, which means that how much is the maximum loss of a portfolio from a peak to a trough. And we test on monthly ones. Data is from 2015 to 2020, S&P 500 and cryptocurrency. Here we don't know the Pickens dependence function because there is no way that you know because it's not synthetically generated. But we can look at the survival probability. And survival probability in a window of time would have heavily biased estimators. But what we see is that our method shows the convexity. These are the level sets of it that all the other methods don't have, is that the Dmax decreasingness. And you can see it, for instance, in multiple dimensions, the two-dimensional cuts of this Pickens surface, and we'll see that ours always satisfies the property that Pickens estimator should have and beats everything, again, significant. So I know that I don't have much of a time, so I just say that just we could now use that to estimate the data. So one thing that I want just to say very quickly is that now you could train a GAN, and that's what we did, to estimate this spectral measure and generate synthetic like extreme data. And I don't go through the details, they're in the slides. You're more than welcome to email me. It is also in the paper and ask questions if you want. But we have a method that now we can generate extreme looking data in very high dimension in real time by learning the Dehaene spectrum. And these are estimators of the fake data generating Pickens estimator and real data generating Pickens estimator. And you will see that they're so close that shows that the fake data that we generate is just as good as real extreme data. Finally, in one last slide that I have, I just say that all I presented right now assume that everything go to extreme together. For instance, earthquake in California and earthquake in Nevada. We have actually generalized this to have some bulk data, like a smaller earthquake and some larger earthquake. And we use the methods that we invented based on Archimax Copula. Papers are given here that we could even generate extreme looking data from non-extreme data. And given the fact that I don't have time, I'm going to stop by here and thank you again, Eric and everybody, Ms. Barner, Doran, Dr. Doran, for inviting me. Very honored to be here and thank you for supporting me over many years. So I'm happy to answer questions.
Okay, so we have the question and answer. First question is like from Fred. I had something similar, right? He's saying that you consider representations to see what is preserved, because if you're saying there's an equivalent representation, you're assuming that the equivalence relations or isomorphism happen, right?
I see.
And so
that's an excellent question. So the question is, if I am given a phenomena, when I have a latent domain, if I make a diffeomorphism of that latent domain in the same dimension, so because it's 1-to-1 or on-to, the other representation is really equivalent to the first representation because you have an invertible, right, a mapping between them. So what you want to prove is identifiability up to a certain diffeomorphism or solid actions in plane or higher dimensions. In some cases, we have been able to prove this identifiability result, but generally in the theory of neural networks, that is lacking. And there is not a unique representation generally, because you can have, for instance, different Google nets and some other ResNet applied to the same image, get different representation and still use them to classify. But definitely In some cases, we have been able to prove, and that's an excellent question, uniqueness up to that diffeomorphism.
So having done a lot in heavy tail analysis for extreme events like in radar, then other distributions like the log normal, Raleigh distributions, and others, right? They can all be mapped from the Weibull distribution. So does this Pickens capability lead into other known distributions that are well used in certain sensing phenomenology?
That is an excellent question again. So there are two ways to do extremes. One is that you use the empirical data and you look at their maxima and you want to model it in tail, and that's what we are doing, and that leads to these three distributions. There's another way of doing it, and that is that you postulate a model. Like, for instance, you say, this is my data. Somehow I believe that this model is good, and I'm going to obtain the parameters for that model. So necessarily they don't immediately relate to each other, but there are models that go in between. So when I said we have like some bulk data and some extreme data, and we interpolate in between and create new extreme looking data, that is a model that goes between non-extreme and extreme, is called Archimax model. Now, people empirically, for instance, match log normal distributions. Of course, it is a model that they chose. What we do, we don't choose the model. We let the machine decide what the model is. So that is kind of like what the neural network in general do. They let, if you do a modeling first, you could do something like, say, I do an AR model or an ARMA model for measurements. It is good if the model actually is chosen carefully by experts. But the idea is that if the model is not chosen by expert and the machine learns it, you may do even better. That is what happened, for instance, in ImageNet. People use Fourier transform, JPEG, MPEG, all of those things. For years, IEEE signal processing people use Fourier methods. It worked. In a speech, methods worked, but they had their own limitation. Once you choose and you let the machine decide what the model should be, there were improvements. So now the question is, if we are going to apply this model to radar, can we beat log normal distribution or not? That is something that we haven't investigated, definitely worth an investigation on its own, in my opinion.
So I guess the last question here from Rob Martin is, would you be able to use this, say you have your learning from the machine, but only sampling at the tails to get to the extreme events that are at the tail?
Yeah, that's what we did. Actually, I was going to talk about it, but I ran out of time. So once we learned that Pickens distribution function, right? And we learned the Dehaene spectra, we could sample from the tail. In that case, we assume that all of the events are going to extreme together. Like maybe you have two earthquakes above 6 Richters, one in Nevada and one in California. It is also possible by using a family called the Archimax family that it smoothly estimates between non-extreme and extreme events. So it has all of these methods like Archimedean copulas and extreme value copulas all together integrated to learn these things and sample from them with a mixture of bulk and extreme data. And all of these things are possible. And in fact, I think I have put two papers here that, let me see if I have it. Yeah, here, that you could actually look, and they're published, that, and if you, I will be very happy to answer your questions, and you can email me about it, that actually do that, exactly sample from the tails using limited data from the tail. Now, of course, the more data that you have from the tail, the better. So it is at the end machine learning. So depends on the data, how much data you have.
Okay, well, I'm sure we will all have more questions, right? I have a lot on the cupola that we apply to different things. So in this case, we appreciate everyone who attended today for this distinguished lecture. If you want the slides, you can, I guess, Dr. Tarokh, you can send them to me, and we'll post them at AFOSR. Cindy can have them for distribution. And we want to thank you for all the great work you're doing for many people, not only within AFOSR, but across the DoD, and for a lot of the students that you've trained who also will go on and make contributions.
Well, thank you very much once again, everybody, Eric and everybody. I really appreciate the years of support that you have given me. Thank you for giving me the opportunity. It has been an honor working for you.
Thank you. Well, with that being said, I'm going to end the session for everybody. And thank you, and y'all have a great day. Bye-bye.
Thank you very much again for all your work. Have a
My
good day.
pleasure.
Okay.
Thank you.
Thank you.